welcome everybody to the fourth talk of our seminar in Quantum Mobile Network. Before moving on to today's presentation, I would like to ask the audience if there is any question regarding last week's presentation content. Okay, so for the students who need to get study credits for this seminar, I have added in the chat a link to the exercises and to the talk evaluation sheet. So don't forget to fill in the evaluation sheet and to solve the exercises before the deadline you can find on the Ilias portal. So we can move on to today's presentation. So today we have our fourth talk titled Routing in Quantum Mobile Networks. Presenters are Diego Medeiros de Abreu from the Federal University of Pará, Brazil, Prateek Mantri from the University of Massachusetts Amherst, USA, and Giuseppe Verduci from University Mediterraneo of Reggio, Calabria, Italy. The duration of the talk, as usual, is around 30 minutes and will be followed by a 15-minute question and answer session at the end. The presenters can either send me questions in the chat and I will take them at the end of the session, or they can also directly ask them at the end of the session during the Q&A session. Okay, so the first presenter may now share their screen, their presentation, and you may start your talk.
So, hello, everyone. I'm Prateek Mantri. I'm from University of Massachusetts Amherst, and my teammates Giuseppe and Diego. And today we are going to present on routing in quantum mobile networks. The outline of today's presentation would be we'd start with some introduction and motivation, and then jump into routing in quantum networks, and then move on to how routing would happen in quantum mobile networks, and then some summary and challenges, and then last questions. However, feel free to interrupt in between if something is not clear. I'd be happy to take the questions as they come. All right. So we all know networks are complex, and for reaching from one point to the other point in a network, we need to select a path. This path selection becomes a difficult problem as networks grow larger and larger, and we have to think about problems like quality of service, fairness in terms of distribution of resources to different parties who are using that network, or utility maximization. Problems like load balancing start coming up when we want to make sure that parts of the network are not congested, and we have to make sure that our networks also adapt to the changing topologies. Some routers, some machines may go down, and new path needs to be selected, or as paths become congested, different paths need to be selected. So these problems are something that classical networks have always dealt on, and there are already solutions that exist in the classical network world in terms of how to solve these problems. In classical networks, this is something which is very basic. So there are ways to route traffic where we either use a link state protocol, where we have information about the complete topology and the link cost, and then we calculate how much cost it takes from for a particular path from going point A to point B. Or if the entire topology is not known and the knowledge of only the neighbors are known, then through an iterative process of computation, this knowledge can be exchanged, and an idea about the different cost of different paths can be known. So we use Dijkstra, for example, for a link state protocol, or Bellman-Ford for distant vector protocol. And these diagrams are just trying to explain how these different costs are computed. However, in the quantum world, there are different problems that are associated. As we saw in earlier presentations, that you can't copy a qubit because of the no cloning theorem. And unlike classical communications, you can't increase the rate by just increasing transmission power. There are fundamental limits to the amount of information that can be sent, mostly due to problems of erasures or the decay, which decay along, for example, if you're using an optical fiber cable, there is a decay which happens exponentially. These transmission losses lead to fidelity decreases. Work by Masahiro Tokoida, Saiket Buha, and Mark Wilde, and subsequent work by Perendola et al. Talk about a fundamental limit and upper bound in terms of information that can be sent through these kind of channels. And these fundamentally limit in terms of how much information you should be able to share. Also, unlike classical information flow, when we talk about routing entanglement flow is also directionless. And that becomes an interesting question to solve in terms of how routing would happen in networks like this. There are multiple routing paradigms. Today, I'm going to only talk about two of these. One which is called as teleportation-based, and the other as entanglement-based routing. In teleportation-based routing, we use shared entanglement parties to teleport quantum or classical information. It mostly looks like in a linear network, it would look like this. So we have a midpoint source, and we send we use a midpoint source to send entangled photons to two of these parties, and then they share an entanglement link. This link can be shared between different repeater chains, and then you use an entanglement swapping operation to create an end-to-end link. These midpoint sources here can also be replaced by a meet-in-the-middle protocol, where we generate entangled photons at each of these repeater nodes and send one of those entangled photons to a middle station. And then we erase the which path information and creating an end-to-end, creating a link between the two repeater stations. This is what we call as a two-way scheme of entanglement generation. So this can be iteratively done over over the entire chain of the network. However, we can also send this information only in one direction. So you have one repeater chain, and then you encode this information, and then send it to the next repeater chain, and use use different kinds of protocols. So in this paper by Sri Raman Muralidharan, they use teleportation-based error correction to have an encoded psi-L, and then use a logical teleportation circuit to get your psi-L out. It is postulated that these kind of protocols can help you beat these fundamental bounds that I talked about, the TGW bound or the flop bound, and you can get a much higher rate of the secret key sharing using protocols like this. The other kind of routing that happens is what we call as the entanglement-based routing. Because of this new nature of quantum entanglement, you can share entangled state, and you can use different kinds of measurements to create arbitrary different kinds of graphs from any sort of arbitrary graph state. You can also use multipartite entangled state to achieve long distance parallel communication. Which makes us wonder like how this really happens. So for example, you have an n-qubit GHZ state. An n-qubit GHZ state is just a generalization of a Bell state to multiple qubits. There also exist other kinds of multipartite entanglement, but for the discussion purposes, I'm just going to stick to GHZ states. So you have an n-qubit GHZ state, and you perform an X-basis measurement, and using this, you can have an n-1 GHZ state, as we see over here. You can also do a fusion measurement, upon which success you can create, let's say you start with a 3-qubit GHZ, two 3-qubit GHZ state and one 4-qubit GHZ state. You can use a 3-fusion measurement to create a 7-qubit GHZ state. Or even if it leads to failure, you end up with an n-1 qubit GHZ state at different parties. Han et al. 2019 show that you can create any sort of arbitrary topology or any sort of end-to-end entanglement between an arbitrary graph state using X and Z measurements. Just in terms of showing how this would work, for example, we have an arbitrary topology like this, and there is some sort of entanglement share. So here the red dots are the qubits, and the black lines show the entangled link between these qubits. The red triangles or the green ones show the success event, and the red ones show the failure events. Now, using these measurements, you can create a three-qubit GHZ state and a Bell state between Alice and Bob, doing different kinds of measurements. The point that I'm trying to impress upon here is that you can use entanglement to create, to route traffic in a different manner, which is fundamentally different from how routing would happen in classical states. Now, the question that really comes is, why do we want to use mobile networks? Even with all these repeaters and different schemes, we are not able to go very far with ground-based networks. The intercontinental fiber-based quantum networks are difficult to implement, even with repeaters. You require very closely spaced repeater chains. You require a lot of money. And the distance still scales with proportional to this exponential constant. L naught over here is the repeater spacing, and L attenuation for a telecom band wavelength, which is around 1550 nanometer, comes around to be 22 kilometers. So this fundamental distance scaling factor still remains, which in free space is different. So you can use the properties of free space to get over this highly prohibitive distance scaling constant. You can also have integrated mobile networks, some sort of a satellite and ground-based network integration can allow us to go further. In this paper by Yaocha, they are trying to create a 4,600 kilometer network using between Xinjiang and Shanghai using satellite and ground-based stations, which allows us to go further. We can also have a different spin on these mobile networks. So instead of just using our satellites as midpoint source, we can also have satellites that also act as repeaters and then only interact with the ground stations at end-to-end. And in this paper by Carlo Leoni, they analyze this open space versus open space ground and ground connections. The n equal to 0, 1, 2, 3 here talk about the different kinds of nesting levels that exist. And they show that for an open space network, you are able to have a very high rate, at least for shorter distances. And then they also look into, for longer distances, how this behavior happens. So you can basically use these satellites both as midpoint stations, also or over entire open space network to create longer distances communication. I'll let Giuseppe take over from him.
Thank you, Prateek. Hello to everyone. My name is Giuseppe Verduci from Medeiros University of Reggio, Calabria. And now I will introduce you the MANET, and I will explain you why the conventional routing doesn't work for this kind of network. Okay. So we have these two protocols, distant vector, that base their decision on the best path to a given destination based on the distance. And distance is usually measured in hops. And link state base have a complete picture of the network, the topology. So why these protocols are not good? We have some problems. For distant vector, we have the count to infinity problem and slow convergence, and loop information during temporary nodes failures and network partitions. And for link states are protocols that use flooding techniques that create excessive traffic and control overhead. So why is routing in manets different? The manets are self-organizing networks, and they need for distributed algorithm, and there is no external network setup. The topology change dynamically, so mobile node that joining or leaving, and rate of link failure repair due to node mobility may be very high, because faster nodes create more frequent link breaks. And network partitions, due to the random movements of nodes, the network can be partitioned in non-communicating portion. Asymmetric links, links may be unidirectional. Limited bandwidth, reduce even more due to exchange of routing information. And the last one is new performance criteria. So number of hops, delay, available bandwidth, route stability despite mobility, and energy consumption. In mobile ad hoc network, nodes don't know the topology of their network. Instead, they have to discover it by their own, because the topology is dynamic. The basic rules is that a new node, whenever it enters into an ad hoc network, must announce its arrival and presence, and should also listen to similar announcement broadcasts made by the other mobile nodes. Okay, so we have topology-based routing, and there are three approaches: proactive approach, reactive approach, and hybrid approach. And here we have protocols like OLSR or AODB, and then we have position-based routing. And LAR is an example. We will focus our attention in topology-based routing protocols, and let's explain how work this approach. First, I will talk you the proactive approach, and these are also known as table-driven routing protocols. Each mobile node maintains a separate routing table, which contains the information of the route to all the possible destination mobile nodes. Since the topology of the ad hoc network is dynamic, these routing tables are updated periodically, and when then topology change. It has a limitation that it doesn't work well for the large networks, as the entries in the routing table, because they become too large, since they need to maintain the route information to all possible nodes. We have pro, like immediately available path, and each node has an up-to-date view of the network topology, and cons, like large routing tables, low scalability, high bandwidth, and energy consumption due to the periodic update. The second one is the reactive approach. These are also known as on-demand routing protocol. In this type of routing, the route is discovered only when it is required or needed. The process of the route discovery occurs by flooding the route request packets through the mobile network. And it consists of two major phases, namely the route discovery phase and route maintenance phase. And here we have pro, like paths are only computed on demand, no need for periodic updates, energy and bandwidth saving, and nodes may go in sleep mode. And cons, longer path setup delays, path research efficiency depends on the node mobility, and need of memory to keep discover path, longer path packet header to store path. The last one is the hybrid approach, and it's basically combining the advantage of both reactive and proactive routing protocols. Okay, well, what's new in QMNs? First, we have quantum mechanics. So in classical computer, we were using binary bits 0 or 1, while in quantum computer, we make use of both 0 and 1 by encoding them with within between various DAs. But providing large number of possibility for storing data. As we know, with the help of 0 and 1, we can make only 4 combinations, but with the help of qubits, we can make 2 raised to n combination. We can do parallel processing practically with quantum computers. Quantum entanglement is a special case of superposition in which we define qubits as a reference to each other where the particles can be shared or they can be spatially separated. The quantum measurement can be considered as measuring the value of qubits that can be either 0 or 1. And we consider that qubits collapse toward either or 1. Mobile ad hoc network is a type of network that uses the concept of decentralization. When the nodes are in reach of one another, they can create direct communication. And if they are located far from each other, we have an indirect connection. In Manets, all the nodes are free to join and leave the network. And all the nodes that are joining can take part in communication, either as source or destination. Whenever a node is moving from one point to another, and wants to access some service with the help of service provider, some applications like lost due to the mobility. But with the advent of quantum adaptation, some applications like quantum key distribution and super-desk coding are used. Quantum manets can enhance the concept of quantum communication by using an EPR pair, also called the Bell states in superimposed states. Here we have a comparison between 2 papers which explain the 2 approaches and how to optimize the reference protocol. And in particular, I will describe how a reactive protocols works. So for the second one. Quantum communication schemas are mainly classified in 2 categories: quantum key distribution and quantum teleportation. When using quantum teleportation to transmit quantum bits, the current general method is to first establish a classical channel on the classical channel communication network, and then establish a quantum channel on the path node of the classical channel by using EPR pairs, and finally transmits qubit through quantum measurement and recovery. Nodes can construct the network by themselves with high flexibility, and security is a major problem faced by wireless ad hoc network. The application of the quantum teleportation technology to wireless ad hoc networks can not only solve the security problem, but also improve the network capacity. And routing protocol is one of the key technologies of a network. So the quantum wireless ad hoc networks adopts the on-demand routing protocol in this case. Based on the ordinary ad hoc network, this network assumes that each node has a quantum communication function, including the capacity of holding and manipulating EPR pairs, and they support classical communication at the same time. In the next slide that I will show you, the dotted line represents the quantum channel, and the solid line represents the classic wireless channel. In quantum wireless ad hoc network, when a source node needs to deliver qubits to a destination node, the general method of the on-demand routing works like this. The source node broadcasts route request message to the neighboring nodes, and the route request message contains the source address, destination address, and other information for the route. And each node checks whether it is the destination node, and if not, after checking that the message is not repeated, it adds its address to the message and set it to neighboring nodes, like this. And if yes, it sends a route request reply message. So the destination node may receive multiple route discovery messages from different paths. The destination node chooses an optimal path based on the routing metrics recorded in the received message. The destination node then sends a route reply message back to the source node along the reverse path. The reverse path is the reverse order of the nodes recorded in the route request message. After receiving the route reply message, the source node records the path in its routing table, and the routing is created. Then the source node sends the QCR message along the forward path to establish the quantum entanglement, and after the establishment of the quantum channel, qubits can be transferred by entanglement swap. So what's now with how is this protocol optimized? Using the reverse synchronization method. When the destination node sends the route reply message to the source node, it carries, called as a piggyback, the QCR in the message. And a quantum entanglement is initiated synchronously on the reverse path node to establish the quantum channel. The improved method is based on the fact that the destination node already knows the routing path after selecting the optimal path, and it is not necessary to wait until the source node receives the route reply message to initiate the quantum channel establishment process. And this method, as I said, is called the reverse synchronization method. Here we have a table that shows you the format of route request quantum packet message and a route reply packet message, and you can see there is a QCR field in the quantum route reply packet message. In quantum wireless ad hoc communication networks, on the one hand, node movement and APR pairs consumption may lead to change the network topology, interruption of selected path, and failure of information transmission. On the other hand, the unknown quantum states cannot be copied and retransmitted due to this principle of quantum non-cloning. Before the source node starts to transmit the quantum state, it needs to determine whether the nodes on the current path are still valid for the transmission. When the source node has quantum communication demand, if there is a quantum path to the destination node in the routing table, it will send a path verification request to the destination node along the path through the classical wireless channel, and to verify whether the path is effective. If it works, communication can occur, and if it fails, the quantum path needs to be re-established. That is the process of initiating route discovery as described. So the universal applicability of the reverse synchronization method is verified through the protocol performance analysis and compare with the quantum channel establishment after the forward routing is established. This method reduces the quantum channel establishment time and the number of messages. So it improves the efficiency, but routing in quantum networks is more complicated because it's not only based on the path length, const, and throughput, but it must also take into account the desired end-to-end fidelity. And the next step is to model these protocols and evaluate their effectiveness by simulation. Okay, I thank you. And now is Diego.
So hello, everyone. I think you all can see my screen now. Okay, so my name is Diego from Federal University of Pará. I'm going to talk about the quantum mobile in terms of satellites. So we see the presentation of Giuseppe. We talk about MANET, so they are ad hoc networks. So the question of mobility is a little bit issue there. When you're talking about satellites, we have a very good perspective in terms of research because we already have some satellites being implemented by, such as the MICER satellite by the Chinese. So this is really good research topic. So in terms of mobility, when we can say that each satellite has a fixed mobility in comparison with MANETs. Let me explain this. So I can use traditional Dastra and Belmont 4 algorithms, such as what we have in classical networks, because each node in a satellite node has its own traditional node. So we already know how to track that path. So we can say that compared with MANETs, the node is quite fixed. A good thing from satellites is that it provides global coverage. So if you're thinking about one satellite, it has local limitations, so it doesn't provide global coverage, but we can use what we call a constellation of satellites, so that will be able to provide a global coverage. And one issue that we have with satellites is that the same satellite can only be available for a limited part of time from the ground station. So we can say that the link between the ground and the LEO satellite can expire. So that raises the questions of how to precisely allocate your transmissions. This is a very good question in terms of physical implementation. We have addressed this in the first presentation seminar. So if you're good to check it out if you're interested on physical implementation of satellites. So today we're going to talk about 3 papers very shortly. And they'll address the issues of routing in satellites. So yeah. So these images here is to illustrate how we can compare mobile in different levels. So the first level will be a terrestrial layer where you have optical fibers, quantum networks. The second layer will be the aerial layer where you have most of the MANETs, such as maybe UAVs, drones. And then the final layer, you would have the space layer. This is where you find the satellites. So when you are down here in the terrestrial layer, you can have high key rates, you can have really good maturity in terms of the networks, but you do have limited coverage and you deal with a statistical topology. When you're doing in the space, you can have a global coverage in the constellations of satellites. However, you are limited with the orbits of the satellites. You are affected by weather conditions. You do have a limited key rate, such as because of the distance, and they are relatively expensive when comparing to one single terrestrial network. The first paper that we're talking about address this issue is Entangled MetSat from 2022. It provides us a view of a satellite constellation. So with a satellite constellation, as I said, we can have global coverage of a quantum networks. So it works like this. You have one ground station that will transmit the quantum information. establish entanglement or QPD applications. And you have to choose which satellite you're going to be using in your route in order to transmit your information to another ground station. This is particularly difficult because the satellite has to be able to do all the satellites you choose has to be available for you during the time that you need to do your application, and also you have to do this on time that you need for the application on the other side. So the question which satellites to choose is very important, and now also how long it takes to do all of the communication. And you also have to choose between a trade-off between efficiency and accuracy in terms of time, in terms of the quality of the link that you're using. In this paper, they use a two-step routing protocol, which is based how they find a path is based on a Belmont approach. As I said, different formats, you can use those traditional routing protocols, which is based in distance vector and has a local knowledge of the network. So the first step is to choose what satellites that you are used first. So how do you choose this? You actually get the closest satellites that you have. You can compute the distance choosing of the satellite. And when you use the zenith, which is references to a direct line between the ground station to this angle here, and you can compute the distance to the satellite. The satellite that you want to the ones that keep the maximum transmission fidelity as possible. Also, how do you know where the satellite is also a good question. You can use a pre-configured mapping, so you can have an offline when you don't have to compute every time where the satellite is. However, as we said before, satellites are affected by weather conditions. You can model this in the simulation. And also, if the satellite is already being used by another ground station or for previous situation is not available, you have to do some sort of online mapping to know what satellites is available. So this paper, they propose a hybrid proposal here that use both online and offline, and get a good trade-off between low computational cost and offline, and also a good accuracy. The second question is how much time the road needs to be on. There's a few things that you have considered. You have to consider the transmission of the photon, you have to consider the delay existence in terms of the repeaters. You also, in the terms of the commutation time, is the time that the satellite will change from one direction to another one. So these are something that are interesting in this paper, how they consider it, what satellite to choose and how they perform the route selection. Another paper here tackles the issue of the coverage of the satellite. So we have two types of satellites. We have the low orbit satellites, we're called LEO, and we have the geostationary Earth orbit satellites. So we have satellites that are very low orbits, and we have the ones that are high orbits. The ones that have low orbits have a limit time of the day that they are available for the ground station, but the geo ones, they can be used all day continuously. However, because the one is higher, you have a low key generation. So you have better transmissions with the satellites that are in the low orbits. So how do you do this? How do you use those informations to have a better coverage and also a good transmissions? The idea of this paper was to use both of them and create what they call a geo-link between both of the satellites. So the way that they used to choose the path is using Dastra. So now they have a global knowledge of the networks. And also the main proposal here is that you can use a link between the two satellites. So you not only have a link between the ground station to the satellites, but you have links between different layers of satellites. So this is what we have in this image here. One is with geolinks and the other one is without geolinks. So this is the main idea of the paper here. The issue is what is done here is that when you have two layers of satellites, you can choose either one of those to be used in your transmission. If you go in the path going to ground base to a LEO one and then to a GEO one, you can move faster and then have maybe some better transmission here. If you don't have this, you have to go all from the ground station to the GEO station, but you're going to lose a lot of things in terms of transmission because of the distance. So this is some of the results that they have, the simulated topology of the network. So you're interested in doing research, this is one thing that you can do. You can use some simulators here that use satellite simulations. This is some results that they get. They say that it's really good when you have the double link in terms of when you increase the traffic load, you have a higher success probability. And when you increase the traffic load, with the double layer, you don't have too many hops in the way. So you don't want to have to use multiple satellites in your route. You want to use the at least ones that you can use. So in this way, you can have more available satellites for other transmissions. So you don't want to be spending all the satellites to do just one transmission. So this is interesting result that they have. The final paper that we're going to talk today is called Towards Quantum Satellite Internet Working in Software-Defined Networking. So when we talk about routing this day in classical networks, we do talk about software-defined networks. It's a paradigm that differentiates between the control plane and the data plane. And this is very aligned with what 5G would be expected. So this is a nice field to research in terms of quantum networking. So on the control plane is responsible for all the signaling, controlling operations that you're going to have, in also choosing which path that you're going to use in the routing scheme. It is done by having a centralized SDN controller. This decentralized controller will have a global knowledge of the networks. Also, on the data plane is where the quantum channel will happen. So the quantum channel is responsible to the data plane in the quantum network will be responsible to create the bell pairs, the photon transmissions, QPD applications, and entanglement generation, all of the stuff that relates to quantum will be in the data plane. And the control plane will be responsible for signaling operation and also all of this information. So this paper tackled this issue here. Also compared to different strategies. So they are all what they call, so tackle the difference between using a centralized strategy in this simulation scheme using the Astra algorithm and also two distributed one. So the Astra is the centralized one, the distributed ones are the end colony optimization. Many of you might know this from classical networks and also from optimization and machine learning scheme, and also modified random walk is also a traditional very classical way that you can approach routing. So the result that they get is really good. So what they have here is that when you use Dastra, you have many hop, you have less hops to be using. So you don't use too many satellites when you're using this centralized approach. So this is the main thing that they're selling here. And also in terms of entanglement rates, you have higher entanglement rate if you increase the distance here. This is the data that they use to generate the results. So this might be interesting for you to be looking up on. So in summary, if you can get some things from our presentations, first one is that routing quantum networks, it is different from classical networks. However, you can use some approaches that you have in classical networks. You don't have to revise everything that you learned from classical routing. However, you do have to use some constraints and have some understanding what's going on in a quantum world. Also, in terms of quantum mobile networks, we talk about managed networks and we talk about satellite networks. There are two approaches. They have difference in terms of topology and what metrics you can use and also what algorithms you can use. Finally, we have some open challenges. This is something that we, while we were learning and while we were studying, we realized there is still need for a physical web metrics considered. So few of this paper actually use fidelity and consider also memory and other stuff that already been considered in classic in terrestrial quantum networks. This is still not something that we didn't find in mobile networks. And also most of these papers just use QKD applications or teleportation-based routing. We haven't seen any entanglement-based routing in mobile networks. So these are big open challenges here that we find out in this work. So thank you very much. And we have put some of the questions here, but we can also have the other questions from the audience. Thank you.
Thank you so much, all of you, for your presentation. It was really nice and insightful. So we can now move to the question and answer session. So is there anybody from the audience has a question for the speakers?
Yes.
Yes.
Yeah, sorry. I saw Antonio had there. Okay, sorry. Well, I start. So about you mentioned at the end. So for instance, this scheme where there was two layers, or there were two layers of satellites, so LEO and GEO. So this was specifically for QKD, if I understood, by establishing a key between the ground and a satellite. Or is this right?
Yeah. So in this scheme, they use QKD. As I said, I think one way is that because the experiment that was done in satellite, the mission satellite was about QKD, but we still have a lot to learn in terms of other applications here. So this paper was specifically about QKD, but I think we can use other applications and try to see like do entanglement in this.
Okay. But maybe this is related to your point, because if you think of entanglement, I guess that the, let's say, the figures of merit or the criteria will be different compared to QKD. So QKD, you may, okay, what is the key rate established or something like this? Whereas QKD, for entanglement distribution, you need some kind of more stringent fidelity or, okay, it's just a remark.
Yeah. But this is, I think you're right. Yeah.
Thank you.
More questions? Yes.
Hi. Congratulations, guys. Very good presentation. Well, one question: how to choose the best strategy to routing, teleportation or entanglement? How to decide this? When you can talk about it?
I think like it depends upon your application. So if you are only interested in having, like, you already know what your endpoints are and you're only interested in having your throughput maximized, then probably should go for teleportation based routing. But if you're having an evolving topology and you can use certain ideas around multipartite entanglement that you want to have, let's say quantum private sharing is one of the applications. So you do not want any other party to know which parties get the secret messages. So in that case, a multipartite entanglement or entanglement-based routing would be an interesting application or an interesting way to go about it.
Great.
Does that
Thank you.
Yeah, more questions? Maybe from the students, that would be great. From okay, maybe meanwhile I have a question in the, maybe while the students can think of something. So here regarding the mobility aspect, so when a couple of nodes they share some sort of entanglement state, the scale, I mean the time scale at which the physical mobility happen, at least with the current technology we have, is much different than the time at which the quantum information can be stored on a certain node. So how do they, can you expand a bit more on the interplay between the quality of the quantum memory we have so far and the possibility of delaying the measurement so that the two entanglements are collapsed, so to exchange qubits on a larger range?
There are some physical platforms where you can store your qubits for a longer duration. Trapped ions, for example, become really good about that. But with every physical technology, there is some sort of limitation. So you need to see what is that you are trying to maximize. So is it more about its optical nature, being able to transmit photons easily, or is it more about storage? So I think like the key, at least in the NISQ era, the near intermediate quantum era, we would have to think about what is the objective that we are trying to fulfill, and then choose our technology based on that.
Okay, thanks. Any other comment for or question from the audience? Yes.
Well, I have a question about QMNs to Giuseppe. Why AUDV is not in your slide? You compare OLSR and AUDV. You mentioned reduced simulations, and you mark with a negative. You can explain better this slide?
Okay, you mean about the table when I compare OLSR and AODV?
Yes.
Because I will explain how on-demand routing protocol works with the general methods, and it's like DSR. And for AODB, there must be a paper about that. That talks about the optimization and the implementation of this protocol. But in this paper that I viewed, and that I explain how it will optimized. It's based in a general method of dynamic source routing more than AODB.
Okay.
Thank you.
Yes, I guess we have 4 more minutes to get questions if you have any. So at least we complete 1 hour in total. Okay, maybe I can ask one. If I understand correctly, now the current ways in which these the communication is achieved is at least now we have one satellite that's established entanglement between 2 stations, for example. But we know also that to simplify the story, the quality of these links decays exponentially. So one idea would be to increase the number of intermediate satellites so that, if you just halve the size, it's dramatically improves the quality because the decay is exponential. So what's your opinion? Would it be worth to create some sort of bridge of satellites between the 2 end destinations, or what are the limitations of that? Do you think that increasing the number of intermediate satellites would introduce other challenges, or would simply be better?
Well, one thing that we like I saw in some papers is that you can use UAV like drones that you can have for a purpose that you have one application that you're interested in, and you can repurpose that drone node for other purpose that will be less expensive to do, because I think they are all very expensive to be put on place. But also depends of the application revenue or something that you're gonna get in the end. So that's how the cost will be. In terms of physical implementations, as we saw, I think in the first part of the seminar, we have some big challenges because of the links. So if you with more links that you can have more problems, And also I don't think that we saw anything about like errors. So error correction is also a big challenge this year. So much the way I think is how if you put a lot of links in the way, you can have a probability of having errors and having other issues there. I think it will be interesting, like for a global network, to have multiple, like a constellation of satellites, to have drones, to have many ways that you can choose the links. But this is also a big challenge this year. And other thing that I saw, I don't know actually that we have already a physical implementation of entanglement between satellites, maybe between ground station satellites. I see in a lot of papers they talking about the links between satellites, like a link between LEO and GEO, and also between the satellite constellations. I haven't saw anything about physical implementation of that, and even if we have, it's still very new. I think we still need more advance in that part before we say, okay, let's pull the Earth with a lot of nodes there, and then okay, we might have problems with those. I think that kind of the way the technology evolves.
Yes, thanks. I guess also this introduces challenges that are a bit related to the previous talk about media access control. If you have, it would be easy to say, yeah, you put 20 satellites to create a bridge, but then how to share the access to the channel might get challenging. Okay, we also have time. Yeah, please.
In terms of memory, that's something that you said. We were talking in a group. Most of the papers that we have didn't consider it, and that could be a game changing in terms of what they're doing there, and that would be interesting also to be in terms of research. And I think the next presentation we're going to talk about capacity and other stuff and memory, so that would be also something nice to be looking.
Yes, thanks. Maybe you have time for a last question if you have any.
I'm sorry, can you hear me?
Yes.
I couldn't be here before. Yeah, so I have a question. It is regarding the fact that since we do not have an opportunity, at least en masse, to research the whatever quantum protocols, including the routing we can name, I mean, in a real time with real quantum machines. How do you think, is there any possible way to develop routing protocols for quantum machines without actually having these quantum machines in the first place, at least on the first stages? Thank you.
That's a nice question. I think maybe everything in quantum, you do have to do theory first, I think. And then you can try to do some simulation based on the theory. And then if you do have access to some experimental setup, you can do experiments on that. And I think this is what the papers are based upon, the research has been based upon. We do have, I think, I don't have assets, but we do have some networks, quantum networks that have already been implemented. So we don't have like an internet, so it may be on scale, like really good, like huge scale. We could have some other issue that we don't know. I think Prateek wants to talk more about this. I don't know. It's a good question.
I mean, it's a fantastic question, but I think that's where the satellites and like any sort of mobile network would start coming in play. Like we are not limited by the, as I mentioned in my talk as well, like we are not limited by the fundamental scaling factors that we have in ground-based networks. And there are some developments on mobile networks. I talked about the Chinese experiment between different multi-node networks. So I think like that's where the mobile networks would start coming in play, and it's much more promising than any sort of ground-based network would be.
Yeah, thank you.
All right, so if there are no further questions, I guess we can thank the speaker. And for today, this is all. So as usual, for the students who need the study credits for the course, don't forget to fill in the evaluation sheet and the exercises. I will upload the questions today. And then I will see you next Friday for the new talk on capacity. So are the members of the group here, did they have the chance of interacting already? Did you face any problem?
Hello, we are working on the presentation, and when I started, it was a little bit difficult, but because of the papers and the stuff. But Diego also helped us, and I think it's going to work well. Yeah.
Okay, so Diego is also help you with the next performance in QMN.
I think he helped us with the structure of the presentation a little bit. We were a
Okay,
little bit
good.
overwhelmed, but that was
That's
very
good.
nice. Thank you, thank you, Diego.
That's good. Yeah. Maybe we should involve him in the organizers next year for this. Okay. Jokes aside, yeah. So thank you, everybody, for joining today, and I'll see you next week.